Biomedical Image Processing course. Today in this module we will see segmentation of retinal vascular using wavelets and supervised classification. During this module we will focus the theory as well as the implementation part of wavelet and automated assessment for pathologies of the optic fundus initially requires the precise segmentation of the vessels from the background of it so that suitable feature extraction and processing may be performed. Several methods have been developed for vessel segmentation, but visual inspection and evaluation by receiver operating characteristics, that is ROC curve, analysis have shown that there is still room for the improvement in this particular area. Human observers are significantly more accurate than the methods which show flaws around the optic disc and in detection of the thinnest vessel which are newly grow and which may be a part of lesion of microaneurysm. In addition, it is important to have segmentation algorithms that are fast and do not critically depend on configuring several parameters, so that untrained community health workers may utilize this technology. So today is the need of such user-friendly automated system which can be operated by anyone who is simply having a background how to process it. This motivates the use of supervised classification framework that only depends on manually segmented images and can be implemented efficiently. The method and some of the results presented in this module were previously published in a journal paper. Here the method is presented in great detail, including a dense theoretical review, new test and analysis of the results. An open source prototype of an interactive software implementation is also described well, including details on the most important step of the segmentation process. The method developed uses the two-dimensional continuous wavelet transform, that is CWT, coupled with supervised pixel classification into classes vessels and non-vessel type of data. Wavelet detection works similarly to match filters, while at the same time incorporating the scale angle representation specially suited for the detection of blood vessels. A significant problem discussed in some works is the choice of an adequate scale for local detection filters. Filters of different scales have been combined empirically, while many other algorithms work off only one scale. The approach presented here combines wavelet responses from different scales in future vectors, allowing few pixel classification which are based on statistical training classifiers. An essential property of many methods is their foundation on set of rules that deal with specific situation, leading to complex algorithms that are parameter dependent. If number of parameter increases, the complexity of that automated system will also be increased. Even with large number of rule situations such as central vessel reflexes and branching or crossing points usually fail to be dealt with satisfactorily. In turn, the pixel classification approach is conceptually simple and allows the classifier to handle more specific situations, avoiding the formulation of rules and need for parameter adjustment. The approach takes into account only information local to each pixel, leaving space for improvement through the addition of global inference phase. Even so, it is capable of segmenting the complete vascular network and does not depend on user interaction but on available manual segmentation for training. When a manual segmentation process we involved, it's sometimes also called as supervised learning. Algorithm efficiency must be taken into account in practical and real-time applications, leading to specific consideration during method design. Feature generation and classification of all image pixels may turn out to be a slow process depending on the choice of classifier. In the method described in this module, a Bayesian classifier using Gaussian mixture models for class likelihood was evaluated. The classifier shows good result with respect to ROC analysis as it allows for complex decision surfaces while at the same time providing a fast classification phase. If we reduce certain complexity, ultimately the automated developed software will be sped up. This module begins reviewing the theoretical foundation of the segmentation method, including properties of two-dimensional CWT and the two-dimensional Gabor wavelet, as well as the supervised classifier evaluated. This module describes the approach adopted, which combines wavelet features generation with supervised pixel classification. The same module also lays out the experimental evaluation performed, covering the description of image databases and a brief review of ROC analysis, an overview of the open source implementation and graphical user interface developed for test is given in this particular module. Experimental results are presented here, followed by the conclusion in this module containing a discussion and direction for next future work which researcher wanted to extend further. Now we will see some theoretical background which are necessary while going for automated development. Signal analysis may be carried out using transforms capable of emphasizing a signal's relevant properties, allowing processing tasks such as parameter estimation, noise filtering, and feature detection to be performed on the transformed signal. The wavelet transform is an example of such a signal processing tool that is based on the Fourier transform and is the latter linear and invertible. Fourier analysis extract global frequencies from a signal and is therefore appropriate for signals whose properties do not evolve with time, that is stationary signals. However, it is incapable of locating or analyzing frequencies of limited time duration present in non-stationary signals. One of the first attempts to overcome this problem was the short-time Fourier transform, also known as Gabor transform. in which a sliding window function delimits the signal portion to be analyzed by the Fourier transform. Notwithstanding, the STFT is restricted as a constant resolution is used for analyzing all frequencies given by the window size. The wavelet transform varies the size of the limiting window when analyzing different frequencies, giving rise to a multi-resolution analysis. As observed by Geber, the product between the time and frequency resolution is lower bounded. By taking this particular property, it is possible to analyze the image coefficient in all directions. This implies that there is a trade-off between time and frequency resolution. Increasing time precision leads to decreasing frequency precision and vice versa. The wavelet transform is defined to maintain a constant relative bandwidth during analysis. This means that low frequencies are observed through large windows, that is low time precision, high frequency precision, whereas high frequencies are observed through small windows, that is high time precision, low frequency precision. This type of frequency varying behavior is encountered in a great variety of signals, thus explaining the success of wavelet transform. In fact, the development of CWT theory was motivated by the problem of analyzing microseismic signals derived from oil prospecting, which present this type of behavior. Accordingly, the wavelet transform is specially suitable for detecting singularities and analyzing instantaneous frequencies. The CWT is defined as psi u of BA equal to mod of A raised to 1 by 2 integral psi to the power A minus 1 x minus b into f of x dx. Using this formula, we can calculate the singularities and analyzing frequencies, where epsilon is a epsilon r is the scale parameter which relates the analyzing window size to the frequency. B epsilon r is the central time position being examined. Psi is the analyzing wavelet, also called mother wavelet, and psi star denote the complex conjugate of psi function. The transform may be seen as a linear decomposition of the signal as projection onto basis functions psi BA of x equal to psi of A inverse into x minus b. Using this formula, the linear decomposition of wavelet is calculated, each one associated to a given location in time b and scale a. The domain of the transform u of BA is referred to as time scale plane. There are various analyzing wavelets that may be used depending on the kind of information to be extracted from the signal. The Morlet wavelet is defined as a Gaussian modulated by a complex exponential of frequency k0, where the formula expressed as psi of x equal to g of x exponent to the power minus I k0x plus correction factor, where g of x is a Gaussian function, I equal to under root minus 1, and the correction term is included to the guarantee the wavelet admissibility condition, which is zero mean. The wavelet definition shows a strong relation to the ST of t, also minimizing the time frequency joint uncertainty. Wavelet theory represents a unified view of various signal processing techniques developed independently in fields such as pure mathematics, physics and engineering field too. Being a versatile tool, it is applied to a wide range of applications such as problems arising in the physics. By considering such wide spectrum of it, it is more useful. In addition to that, it is also used for audio, image and video coding, fractals and shape analysis and biomedical applications such as to detect brain activity from fMRI images. The CWT may be extended to higher dimensional spaces, allowing for instance the analysis of images, that is two-dimensional signals, and video sequences, that is time varying 2D signals which may have a set of frames which is used to give certain actions or activities. This extension of CWT preserve the fundamental properties of the one-dimensional case, being founded on coherent states and group theory. The theoretical framework allows the definition of operations over the wavelet space that preserve notations of symmetry. For the 1D case, the natural operations are translation and dilation, being extended to the two-dimensional case as translation, dilation and rotation. Such type of transformation are implemented in two-dimensional plane. The CWT is mostly used for signal analysis and feature detection, in contrast to the discrete wavelet transform, preferably for data synthesis and compression, yielding very efficient algorithms. The two-dimensional discrete wavelet transform provides orthogonal and bi-orthogonal bases, thus allowing efficient signal representation, while the CWT necessarily leads to a redundant representation of data. However, the two-dimensional DWT is formulated as a tensor product of two one-dimensional schemes. It is therefore restricted to the Cartesian geometry, where directional analysis is much more difficult for extracting directional or oriented features. In contrast, the introduction to the rotation operation in the two-dimensional CWT is specially suited for the analysis of oriented image structure by using so-called directional wavelets. This fact explains the adoption of the 2D CWT with the Gabor wavelet to analyze the blood vessels as proposed in this particular module. The 2D discrete wavelet transform or 2D CWT has been used in a variety of applications in computer vision and image processing, such as analysis of medical and astronomical images, texture identification, age detection and fractal analysis. It seems that 2D CWT is much more useful for variety type of application. There are also imaging application in physical problems such as analysis of geological faults and turbulence in the fluid or detection of dilation and rotation symmetries. Now let us summarize this module. Here we begins with segmentation of retinal vascular using wavelets and supervised classification. We have seen theory and implementation part, theoretical background, the one-dimensional CWT and 2D CWT also we have trying to cover. Now in next successive module, we will go for the 2D CWT, the 2D Gabor wavelet, supervised classification in somewhat more detail. These are certain references, one can use them for extending this work. Thank you very much.